Hi, my name is Harunan, and this is my lab for circuits. So the purpose of the lab was to predict the behavior of circuits with resistors and to use multimeters to measure current and potential difference through the behavior of ohmic resistors and capacitors. The fundamentals we'll be using are Ohm's law, the loop rule, which states that the sum of the potential difference across the whole circuit should be zero, the concept of resistance in series, energy conservation and charge conservation, and the junction law, which states that the current flowing through a junction should be equal to the current flowing out of the junction. Some assumptions I made were that the resistance of ammeters and the resistance of wire are negligible, and the models were the circuits that we created in the lab for each of the experiments. And for the results preview, for experiment 1, I1 equals I2 equals 0.0204 amps, and for experiment 2, the slope was negative 0.0167. For experiment 1, my system I defined as the batteries, the wires, the ammeters, the voltmeters, and the resistors. My surroundings were the table and the rest of the room, and my initial conditions were that the ammeter readings were 0 when the circuit was open and not closed. So some observations I made from the circuit that I created were that I1 equals I2 equals 0.0204 amperes, and that matches our predicted value of both of the ammeter readings being the same. And if we reverse one of the ammeters, it results in the sign of the current being flipped. So when we replace the ammeter with the voltmeter, the remaining ammeter read 0, and the voltmeter read negative 3.07 volts. And this is because voltmeters have a high resistance, which makes the current 0, and to make the loop rule equal 0, the voltmeter has to make up for the potential difference that the battery presents. That's where the negative 3.07 volts comes from. So on the right, I have a little diagram showing the circuit after we remove the voltmeter and close the circuit with another wire. But we do have to note that the resistors between C and D and E and F, they don't have the same resistance as shown on the diagram. And so in the calculations on the left, I've just used them as placeholders. So if we plot that, we can see that A to B is the positive potential difference that the batteries impose, and then C to D and E to F are where the resistors are, and those are where the negative potential differences are that negate the positive potential difference from the battery. When we attach the voltmeter, and we alter the circuit, the ammeter reading didn't change because voltmeters have really high resistance, so very little current flows through, as I mentioned previously. So for experiment 2, my system I defined as the batteries, the wires, the capacitor, and the light bulb. My surroundings were the table and the rest of the room, and the initial conditions were that the current is 0 and the capacitor has 0 charge when the circuit is open and not closed. So some observations I made were that the conventional charge flow is from the bulb to the resistor when the capacitor is being charged, and when it is being discharged, the flow is from the resistor towards the bulb. And I also noticed that the light dimmed over time as the current stabilized, and that's because the capacitor was discharging, which decreases the current flowing through the light bulb. So using the equations on the right, after recording over 20 seconds, I plotted the natural log of the potential difference over time, and that means my slope would be negative 1 over R times C. My R was 0.2 and my C was 30 ohms, which is the batteries. And doing the calculations, I got 0.167. Negative 0.167, I apologize. Some source of error were that I could have read and recorded incorrect values from multimeters, or maybe the batteries are a little worn out, which could have led to inaccurate voltage readings. So for the first question, we actually did this in person, so I'm going to skip the first part of it. But doing with the virtual simulation, the ammeters and wires would really have 0 resistance, whereas in our real life experiment, they could have a value very close to 0, but not 0, and that's why we said that it was negligible, but this means that the simulations would be more accurate than ours. And for the second question, again, we did this lab in real life, so I'm going to skip the first part. But with ideal batteries and ideal capacitors and no resistor, the capacitor should be charged instantly, unlike ours, and the resistance doesn't exist.